Let us first start by examining the shapes of the atomic orbitals for carbon. The 2s atomic orbital is a sphere, and the three 2p atomic orbitals are shaped like dumbbells, oriented along the three axes, 2px, 2py, and 2pz. Think of these four atomic orbitals as three-dimensional shapes, where you are most likely to find an electron 90% of the time. Notice that the electrons have access to both lobes for the 2p orbitals. Starting from the abbreviated electron configuration for carbon, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Although we now have four unpaired electrons for bonding, we still can't explain the experimentally observed bond angles for a tetravalent carbon. Thus, when we mix the 2s atomic orbital with all three 2p atomic orbitals, we create four new degenerate energy hybrid orbitals. The shape of the new Sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes, where you can find the electron 90% of the time. The hybridized carbon now possesses four unpaired valence electrons and is said to be an Sp3 hybridized carbon. When we superimpose all four Sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in three dimensions. The four new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of a tetrahedron with all angles at 109.5 degrees. Your instructor will often draw the Sp3 hybridized carbon on the blackboard as shown. The two solid lines in this drawing are in the plane of the board. The wedge represents the electron coming out of the plane of the board, and the dashed line represents the electron going back behind the plane of the board. Each of the four Sp3 hybrid orbitals contains one electron capable of forming a covalent bond. The Sp3 hybridized carbon is now capable of forming four covalent bonds. Here, X represents any atom with a valence electron capable of forming a covalent bond. Because the electron density is symmetrically located about an imaginary line that runs through the two adjacent nuclei, we call these bonds sigma bonds. An example of a simple carbon compound with an Sp3 hybridized carbon is methane, CH4. The ideal bond angles are all 109.5 degrees, due to all four equal in size hydrogen atoms attempting to get as far away from each other as possible. Your instructor will often draw methane on the blackboard as shown. Again, the two solid lines in this drawing are in the plane of the board. The wedge represents one of the hydrogens coming out of the plane of the board, and the dashed line represents one of the hydrogens going back behind the plane of the board. Another simple carbon compound that utilizes Sp3 carbons is ethane. From the two-dimensional Lewis diagram, we see that each carbon has four single bonds. Thus, both carbons are Sp3 hybridized. Starting with two Sp3 hybridized building blocks, we can start to construct the molecule in three dimensions by forming the CC sigma bond. Next, the six hydrogen sigma bonds are formed, which affords the final three-dimensional structure for ethane. The two-dimensional Lewis diagram for ethane implies that all four bond angles are 90 degrees. However, employing the basic principles of hybridization theory, we see that the bond angles are all nearly 109.5 degrees. Now that the molecular geometry for ethane in three dimensions has been determined, we can begin to examine some of ethane's interesting physical properties. For example, free rotation may occur about the carbon-carbon single bond, which allows us to explore simple conformational analysis. Conformations are different arrangements of atoms due to these rotations. When we place the electron density around each hydrogen atom, we see that the hydrogen atoms from adjacent carbons do not touch. To make this diagram easier to view, we will remove the electron density from 2 of the hydrogen atoms from the back carbon. Even though the hydrogen atoms from adjacent carbons do not touch, there is torsional strain due to the electron clouds of the adjacent carbon-hydrogen bonds, which impedes the rotation about the CC bond. This gives rise to the staggered and eclipsed conformations for ethane. The difference in relative energy between these 2 conformations is approximately 3 kilocalories per mole. It may be easier to remember that atoms want to be as far apart from each other as possible. Think of it as less crowding. When molecules are viewed down the CC sigma bond, we call this a Newman projection. Often you may see your instructor represent the Newman projection on the blackboard as follows. When we replace one of the hydrogen atoms with an atom that has a larger atomic radius than hydrogen, steric factors will arise, which will increase the barrier of rotation. As the dihedral angle changes, so does the relative stability of the molecule.